So the answer that they've given is when D is decreasing instead of increasing. So if you wanted the answer to when it's increasing, it would be on the interval from 0 to 20, union, interval from 30 to 40. That'd be two answers for increasing. Okay, it increases from 0 to 20, and then it's steady, but then it increases again from 30 to 40. So if you answered increasing, you have to give both intervals. They give the answer to where it's decreasing, which is 55 to 75. So either way, that's just a... These questions are made by a group, and then the A+ people change some of the questions and rewrite some of them. That's one that they probably changed the question, but they didn't change the answer. They probably changed it to decreasing. Probably changed it from decreasing to increasing, but kept the answer. Y'all are sure. It's worded wrong. Okay? So whichever way you want to think about answering it, there's that. Anything else from this one we need to talk about? Yep.
Are you supposed to graph at the bottom?
Okay, yeah, that's a good question. All right, this is not the only answer. Okay, this is just an answer. That's why it says a possible answer. So all that has to happen is between -5 and 0, you have to be going down. Between 0 to 2, you have to be going up. And then after 2, you have to be constant.
Okay.
But it doesn't have to be this. It could be, you could make it a line here, all the way to 0. And you could just make it barely increase and then increase very fast. And then it's just going to have some of those same characteristics. That wasn't the question I thought it was. There's one coming up soon that is anything else from here? There was a couple of the questions yesterday from the Check Your Understanding that were tricky, that you guys didn't ask anything about. But the video, I answered them for the other class, I think. So you may want to watch those. Okay, here's today's lesson. How fast does a penny fall from the Empire State Building? A penny is dropped from the top of the Empire State Building from a height of 1,250 feet. The height of the penny in feet, t seconds after it's dropped, is given by the function h of t equals 1250 minus 16t squared. So I'm going to complete the table to show the height of the penny at each of the given times. So can you guys fill out that table without me? See if you can. Did we get 1250 for the first one? I sure hope so. I'll let everybody get the second one. Did everybody get 1186 for the second one? Everybody say it, squared away. Can I show you guys a quick way to find the rest of them in your graphing calculator? If you don't know how to. Y'all ready? Graphing calculator. It's already taking too long. I'm killing you. Ready? Y equals top left. Everybody's good? Make sure this screen, everything's cleared. Make sure none of your plots are selected at the top. Everything cleared out? What was that? Okay. So this would be 1250 minus 16 x squared. The x button is right beside alpha. X comma t comma theta comma n. Is that good? Now let's all click second window, which is going to be table set. That's what we're clicking. Make sure our table start is 0 and our delta table is 1. Second window, that's what I click. Table start is 0, delta table is 1. It's there. Second graph. Here's your table, plug in all those values. So I could go to 2, I get 1186. I go to 4, I get 994. 6 is 674. 8 is 226. They're all right there, and I'm done. Did they do that? Again, that's why those calculators are very important. Okay. Questions there? I have a question that they didn't ask. Is this linear? Do I have equal input intervals? From 0 to 2 is up 2. From 2 to 4 is up 2. From 4 to 6 is up 2. From 6 to 8 is up 2. I have equal input intervals. So to be linear, I must also have equal outputs. This one goes down by 64. This one goes down by 192. 320. This one goes down by 440. 8. So the rate of change is not constant. Therefore, it's not linear. Let's go with that. We can tell that just from the table of values. 2. When's the exact time the penny hits the ground? Exact. Exact. Well, if I look at my table, at 9 seconds, its height is negative 46. So it's sometime between 8 and 9. Does anybody know how to find exactly where? Or are y'all just going to be, what would be y'all strategy?
1,250 divided by 16. And then you take the square root of that.
Okay. So your strategy is you are looking for where the height is 0. So plug in 0 for the height.
Yeah.
That could work. This is a way. So then we could move that over. It becomes positive, which is then what you were saying, divide by 16. t squared equals something. I'm not that interested. Square root,
8.8.
more.
3.8. Or 3.9. They might have to
AP pre-cal test, everything's rounded to 3 decimal points. So don't shortchange it. That's the first time I think we've had one like that. So go to 3 decimal points if you're rounding. So 8.839. Did I follow that way to do it? Can I show you a way to do it on your graphic calculator?
Yes.
Sweet. So there's 2 ways. You do the easier way first. Let's do the easier first. Click graph. Click zoom. Oh, well, that's fine. Make sure you click zoom 6. And then graph, and it looks like field goal uprights, essentially. That's what my graph looks like. Because what do I know about this graph? It's x squared, meaning it's a parabola. It's got a negative a, meaning it opens down. So there should be some vertex, and then on its way back down. So what I care about, though, is where's the height 0? Height is represented by y. So I'm looking for this x-intercept. The x-intercept is when the y value is 0. Does that make sense, what I'm saying? So I can find the x-intercept by clicking second calc, which is the button above trace. Another name for x-intercept is 0, or root, or solution. On your calculator, it's called a 0. So I select 0. And then you see at the bottom it says left bound. Is everybody with me? Are you typing on this thing?
It's about dead.
So much for all this practice we're doing with this calculator. So I'm going to go over left boundary. I just need to pick some point that is left of the x-intercept I care about. So I see it's somewhere between 8 and 9, right? So like my left bound, I'm going to make it be 8.48. I'm going to make my right bound be like 9.6. Doesn't really matter. Then it says guess. So just see how I clicked enter on left bound to go to right bound. I clicked enter on the right bound to go to guess. I'll make this look better in just a second. This does not look great. Click enter again. It tells me the 0 is at 8.8388348, which is what you got here. Doing it with solving instead of graphing. Alright, let's make this look better because this looks awful and everybody just give me the weird look. Let's click window. Right now, the maximum Y value we go to is 10. But we know this starts at 1,250 feet. Right? So let's change the Y max to be 1,500. I don't know if that's going to be great, but it's going to be better. Also, let's change the X minimum while we're at it. Does it make sense to talk about when X is negative? Because we're doing time, we're starting at 0. So let's make the X min 0 on window. Now click graph. Now that is half of the parabola, which is the y's or the height of the penny, x being the time as we go. You see it just kind of slowly falls, faster, 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 because the rates have changed. The slopes of the tangent lines are getting more severe as the penny picks up. Anyways, so from here, let's do all this again. I care about the x-intercept. So let's click second calc 0. Now you see that little cursor that you can see now that you couldn't see before because my graph was just so bad. So left boundary means I just need to pick some point that's to the left of the x-intercept. It doesn't matter where it is. Just pick a point and click enter. And then I'm going over to a right boundary, something that's right of the x-intercept. You'll see the cursor go off the screen in this case because of where we set our boundaries. Click enter. Guess does not matter. Just click enter again. Does that make more sense with what we're doing when you can see the cursor guy move left to right? Are we still lost? Good talk, good talk. Okay, I'll just say it. You got in there. Oh, gosh. How are y'all? All right. 2. When did the penny reach the ground? 8.839 seconds. Everybody's okay with that? 3. Find the A rock in the penny's height for the total length of the drop. Y'all do that one yet? Hopefully y'all know how to do that. I hope. We've done it 3 days now. We've been doing average rate of change. When you see average rate of change, what do you think? Slope. You want the slope of the line for the entire drop. Louder?
How do you do that on a non-straight line?
It doesn't have to be a straight line. You are taking the graph, which was this, right? Whatever. Average rate of change is a secant line. I'll show you use green again. From the beginning to the end, you're connecting those and finding the average rate of change. Because it's going through the graph twice. This is the whole idea of my average rate of change over a big interval versus shrinking the interval to become an instantaneous rate of change. It's still an average rate of change. You guys know your points that I'm plugging in? What was the point at the beginning of the drop? 0, 1250. Right? Point. X and Y. What's the point at the end of the drop? 8.839, comma, 0. Those are my points. The beginning, time was 0, height was 1250. The end, time was 8.839, height was 0. That's the end of the drop because it's on the ground. Can't keep dropping. So what was the change in Y? Negative 1250. What was the change in X? 8.839, which is, I don't know, negative 141.419. And this is in feet per second. Right, because the change in Y is feet. Change in X is seconds. So on average, it was dropping 141 feet every second. But then look, we've already figured out what the intervals were. For the first 2 seconds, it only went down 64 feet. But it averaged going down 141 feet every second. But in 2 seconds, it only went down this much. Right? And in these 2 seconds, it went down 192. And in these 2 seconds, 320, which would be negative 160 feet per second. So we're finally above this. Following what I'm saying if I went down 320 feet in these 2 seconds, that means divide that, it's negative 160 every second on that interval. What we're wanting you to see is it's speeding up. The beats get faster. Right before it hits. Right? It was slow, a little faster, a little faster. Sweet. Determine how many feet the penny fell during each 2 second interval. Oh, I didn't know this was the question. Already did that, right? It's all of these. Sorry, shouldn't have worked ahead. I so wanted to do that. So it fell 64 feet. It fell 192 feet. Then it fell 320 feet. Then it fell 448 feet. Everybody's good with this? So, what do you notice? They want you to notice the number of feet fallen. So, feet fallen is increasing, which means for us, that means it's not constant. And if it's not constant, that means it's not a line, which I already showed you by graphing it. It not be a line. Now, can you find the average rate of change of the height of the penny on each interval?
Can you do this in calculator? Like all of them at once.
No. Not that I know of. But it's not that hard. What's the average rate of change? It's the slope. It's the change in y over change in x. How much did the y's change between 0 and 2? Between 0 and 2. The y's. Negative 64. That's the change in y. How much did the x's change by between 0 and 2? So this is negative 64 over 2, which is negative 32 feet per second. Let's go with that. Change in y over change in x. How much did the y's change between 2 and 4? Negative 192. How much did the x's change by? 2, which gives me negative 96. You good with how to find these? Can I just write them? Negative 160, negative 224. So these are the rates of change for each 2-second interval. The average rate of change. Six, is the penny speeding up, slowing down, or falling at a constant speed? How do you know? Say it again.
Because of feet falling increased every 2 seconds.
Okay, so the amount of feet that were falling over a 2-second interval kept increasing. It kept growing. That's fine. I would take that. Here's what they said. They said the average rate of change over each 2-second interval is getting more negative. Which means it's getting faster. So you were talking more about distance traveled in your answer. They're talking more about the speed in theirs, right? Because it's asking for the speed. But you can relate it, and you explained it well enough that I think yours would have counted. So again, the average rate of changes are getting more negative. You can't say these average rate of changes are increasing because they're not increasing. They are decreasing because they're negative. This all goes back to the conversation we had yesterday about slope being bigger for -8. I said you can't say that. And you said it's steeper for -8 because -2 is bigger than -8. Next is graph h of t. So we kind of already seen this. We've got 0, 12, 50. What's another point? 2, 11, 86, which is here. 4, 9, 94, which is here. My 1186 is terrible, by the way. 1186 would be like here. And then 994 would be, oh, I'm in the wrong spot again. Dang it, y'all aren't helping. 4. 6 should be 674. That's like right in the middle. And then 8 should be at 226. And so I've kind of already shown you this graph. Right, but you should see it's half of a parabola. All right. We've not talked about this in here, but do you know if this graph is concave up or concave down? Don't know. You got a guess?
Concave down.
It is concave down. When a graph is concave up, it looks like it would hold water. If it's concave down, it won't hold water. There's a way you can kind of easily spot it as you're looking. So this one is concave down. Also, what I want you to think about here, think about drawing tangent lines. Everybody remembers what a tangent line is? What's happening to the slopes of all these tangent lines? Right here, this was like negative a quarter, right? And this was like negative 1, and this was like negative 3, and this is like negative 8. I don't know, I'm just making those numbers up as I'm going. What's happening to the slopes of those tangent lines?
It's decreasing.
They're decreasing. So here's what you need to know. Slopes of tangent lines are decreasing. Okay? When graph is concave down, slopes of tangent lines are decreasing. And the converse of this is true, which means if I look and the slopes of tangent lines are decreasing from left to right, then that means it's concave down. Also, the inverse is true. The graph is concave up. Guess what's happening to slopes of tangent lines? They're increasing. And the converse of that is true. If slopes of tangent lines are increasing, then it's concave up. One more thing I got to show you guys. Let me go back to here, and I'm going to write this out as like a table, sideways, because I think we'll see it better. So this is 0, 2, 4, 6, 8, and this was 1250. 1186, 994, 674, 226. Do we have constant changes of our inputs? Up 2, up 2, up 2, and up 2. All right. And then did that produce constant changes in the output? Down 64, down 192, down 320, and down 448. So no, we did not have a constant rate of change. But do you guys remember we talked about the rate of change of the rate of change? We talked about it with a line. What was the rate of change of the rate of change of a line? 0. What I want to do now is I want to find the rates of change of these rates of change. So essentially, what's happening as I go from negative 64 to negative 192?
Decreasing 128.
Down by 128. Is it okay with that? You just subtract them to get there. What about from negative 192 to negative 320?
Negative 128.
What about from negative 320 to negative 448?
Negative 128.
So this has a constant rate of change of its rate of change. But it's not, the rate of change is not zero. Think about, okay, for a line, the rate of change is constant. And the rate of change of the rate of change is zero. What is this graph? I've already said it, this is half of it's a parabola.
Yep.
The rate of change of a parabola wasn't constant. But the rate of change of the rate of change is constant. Meaning the rate of change of the rate of change of the rate of change would be, if I did it again, if I did the rate of change of the rate of change of the rate of change, I would get 0. So, here's the way that you don't have to know it to that level for pre-cal. Here's what you need to know. This here, this line where I find the rate of change, we're going to call that the first difference. Okay? If the first difference is constant, then it's a line. Right? That's what, but it wasn't this time. What was the same was the second difference. The second difference is constant. What's that going to be? A parabola, a quadratic, let's go this. Let's go degree 2 polynomial. We didn't even talk about what a polynomial is yet. What's a line? Do you guys know a line is a degree 1 polynomial? You know how to tell the degree of a polynomial? It's the power,
Oh, wait, yeah, the highest power.
the exponent. Yeah, the highest exponent that you have. So for a line, we know lines are in the form mx plus b. What's the power of x? 1. There is no power, it's understood 1. So it's a first degree polynomial, which makes it be a line. For a second degree polynomial, that's going to be something like ax squared plus bx plus c, which is a parabola, which is a quadratic. If I have a constant third difference, guess what I have? I have a degree 3 polynomial, which is the snake. If I have a constant fourth difference, the